Welcome and congratulations. You are about to spend 5 days learning how professional software teams think before they build. My name is Shandama, and I am going to be your guide through this week. Today is day 1 of our crash course. The topic is systems thinking and requirements. By the end of today, you will be able to look at any software product and describe it in a way that another engineer or even your manager will instantly understand. This week is the bridge between the basic coding you have already done in college and how we actually work at BISTEC. We work with artificial intelligence agents that write a lot of the code for us. That sounds amazing, but it puts the responsibility on us to think clearly about what we want before we ask the AI for it. That is what this week teaches. So take a deep breath. Get a notebook. Let us begin. Here is how the week is laid out. 5 days, 4 hours each. Today, day 1, is about systems thinking and requirements. You will learn what a system actually is and how to capture what a customer wants in a way that does not leave room for confusion. Day 2 is about building blocks. We will learn what an API is, what a database is, what a cache is, and when to use which. These are the Lego pieces of every modern application. Day 3 is about quality, speed, reliability, security, and how we know things are healthy in production. With real numbers, not vague words. Day 4 is about putting everything together end to end. We will draw architecture diagrams, write decision records, and run a proper design review. And day 5 is the bridge. We will learn how to write a specification that is sharp enough to drive an AI coding agent. That is the skill you need before you join your team. Each day, hour 3 is hands-on. By the end of every day, you will have built something you can show. Let me show you exactly what you should be able to do by 5 p.m. today. Number 1, you should be able to define a software system in plain language, not in jargon. Plain language a non-technical person would understand. We will give you 4 keywords to use. Number 2, you should be able to tell the difference between 2 kinds of requirements. The kind that says what the system does and the kind that says how well it does it, with at least 3 examples of each. Number 3, you should be able to take a 1-paragraph description from a customer and turn it into proper user stories. We will use a format called INVEST, which is 6 tests every good user story passes. Number 4, you should be able to draw a context diagram. This is a simple boxes and arrows picture using a method called C4. It shows who uses your system and what your system depends on. And number 5, you should be able to read a vague brief and find the holes. Most customer briefs have hidden assumptions and missing information. Spotting those is half of senior engineering. 5 concrete skills. Every challenge today maps back to one of these. Let me tell you a story I have seen happen many times. A junior developer gets a request. They open their editor and start coding immediately. 2 days later, they show their work. The customer says, "That is not what I asked for." The senior engineer says, "What about errors? What if 2 users do this at once?" The developer has no answer. They start over. Compare that with a developer who spent 30 minutes first writing down what the user actually wants. They drew a small diagram. They asked 2 clarifying questions. Then they coded for 1 day. They walk into review with answers ready. The senior engineer asks them to mentor someone else next month. Same person, same skills. The only difference was 30 minutes of thinking. Now the rule has changed even more. An AI agent can type code in seconds. The expensive part is no longer typing. The expensive part is thinking. If you cannot describe what you want clearly, the AI will build the wrong thing very, very fast. So this whole week is about that thinking skill, because that is now what makes you valuable. Let us start with the most basic word, system. A system is a set of parts that work together to deliver a useful outcome. Three things in that sentence matter. First, parts, the things inside. They could be apps, services, databases, scheduled jobs. We will give them better names in a moment. Second, work together. They are not independent. They send data and signals to each other. They cooperate. If one stops, the others usually feel it. Third, a useful outcome. A user gets something they want. A ride is booked. A payment is made. A class is scheduled. A receipt is filed. This is more than a definition. It is a way of looking at things. When you see a piece of software, train yourself to ask, what are the parts? How do they cooperate? What is the useful outcome? If you can answer those three questions, you understand the system. Let us see this on something everyone in Sri Lanka knows. Look at PickMe, the ride-hailing app. To you, it might feel like one app on your phone, but it is many parts working together. When a rider opens the app and taps a destination, the rider's phone is one part. Somewhere in the cloud, there is a backend that handles bookings. There is a part that finds drivers near you. There is a part that calculates the fare. There is a part that talks to the payment gateway. There is a part that sends a push notification to the driver. There is the driver's phone running a different app. And there is a dashboard that PickMe staff use to handle complaints. All of these are parts. They cooperate by sending messages to each other through the network. The useful outcome is that the rider gets a ride and the driver gets paid. Take any one of these parts away. The notification service, the matching service, the map, the whole experience breaks. That is what cooperation means. Each part has a job, and together they deliver the outcome. When you design software, this is the picture you must hold in your head. Now let us name the parts properly. The first word is component. A component is one focused part of the system that owns one job. I want to give you 3 quick tests so you can recognize a component when you see one. Test 1. Can you describe what it does in a single sentence? If yes, you have a real component. If your sentence has the word and 3 times, it is probably actually 2 or 3 components hiding inside one box. Test 2. Could it be replaced by a different team's version without breaking everything? If yes, the component is well defined. If swapping it would cause chaos, the boundary is fuzzy. Test 3. Does it have a name a non-technical person would understand? Payments, yes. Service 3, no. Good component names tell you what the thing does. They do not need a glossary. If a component passes those 3 tests, you are looking at a clean piece of design. Most of professional system design is just choosing components well. Here are the components inside PickMe. I am not making these up. Most ride-hailing apps have something very similar. The Rider mobile app. One job. Let a rider request, track, and pay for a ride. The Driver mobile app. One job. Receive trip offers, navigate, and report when the trip is done. The Booking service. It creates and tracks trip records. The Matching service. It finds the best driver for a rider's request. The Pricing service. It calculates the fare based on distance, time, and how busy the streets are. The Payment service. It charges the card or wallet, handles refunds when needed. The Notification service. It sends push, SMS, and in-app messages. The Operations dashboard. It lets PickMe staff see what is happening live and intervene when something goes wrong. And finally, the database. It stores users, trips, payments, and history. Notice how each one has a clear single-sentence job. That is what a good component list looks like. The next word is boundary. A boundary is the line between what your team builds and owns and everything else. Inside the boundary, you write the code. You can change it. You decide how it works. And when it breaks at 3 in the morning, you are the one being called. Outside the boundary, somebody else built it. You can only call it through its public interface. You cannot reach in and change it. If it breaks, you wait. You report it. You design your system to keep working as best as it can while the external thing is unavailable. This sounds simple, but choosing the boundary is one of the biggest decisions in any project. Same product, different boundary, different team, different budget, different number of people on call. Drawing the boundary is one of the first things you do as a designer. Let us draw the boundary on PicMe. Inside PicMe's boundary, the booking service, the matching service, the pricing service, the payment service, the notification service, the rider app, the driver app, the operations dashboard, the PicMe database. All of these are built and owned by the PicMe engineering team. Outside PicMe's boundary, Google Maps. Even though PicMe uses Google Maps for routing on every single trip, they did not build Google Maps. They are a customer of Google. Same with the card payment gateway. Same with the SMS provider that sends one-time passwords. Same with the App Store and Play Store where their apps are downloaded. Now here is the important part. If Google Maps goes down, PicMe is in serious trouble. They cannot match drivers without it, but they cannot fix Google Maps. They can only fall back, maybe show old routes, maybe pause new bookings, maybe call Google support and wait. That is what living with a boundary feels like. You take ownership inside, and you design carefully for the outside. Word number 3, actor. An actor is anything outside your system that interacts with it. There are 3 kinds. First, human actors, people with a role. The rider, the driver, the operations agent, the finance approver. Each one has a different reason to use the system and they need different things from it. Second, system actors, other systems calling yours. The payment gateway, the SMS provider. A partner company's a PI. They are not people. They are software talking to your software. Third, time actors. Scheduled triggers. Things like every Monday at 8 in the morning run the driver payouts, or 30 days after a trip is completed, archive the receipt. The trigger is the clock, not a person. When you draw a system, you list all 3 kinds: people, other systems, and time. Forgetting any one of these is a common mistake. Let us list the actors around PicMe. The human actors are the rider, the driver, the operations agent who handles complaints and refunds, and the finance team who pulls daily settlement reports. The system actors are the map provider that gives routes and time estimates, the payment gateway that charges riders, the SMS provider that delivers one-time passwords, and the push notification services like FCM and a PNS that alert phones. And the time actors are the driver payout job that runs every Monday morning, the surge pricing recalculation that runs every 60 seconds, the receipt cleanup that archives anything older than 90 days, and the daily report that fires at 6 a.m. Sri Lanka time. That is 12 actors interacting with one system. That is normal. Real software has lots of actors. Listing them is the first step toward designing well for all of them. The 4th word is interface. This one is the most important. An interface is the agreed way 2 parts talk. Same words, same shape. Both sides understand what to expect. There are 6 kinds of interface you will see all the time. I want to introduce them also. The names are familiar. The REST API. This is what most web and mobile apps use to call backends. It uses HTTP, the same protocol your browser speaks, and it sends data in JSON format. The mobile screen itself is an interface. The user calls the app by tapping buttons and filling in forms. The database query, usually in SQL, is the interface to a relational database. A message queue is when one service drops a message and another service picks it up later. A file or CSV is an old but still common interface. One side writes a file, the other side reads it. And a webhook is when you tell another system, "Call me at this URL when something happens." Each one of these has its own rules and trade-offs. We will use most of them this week. Now I want to give you a very useful trick. 2 ways to look at any system. The black box view. You describe what goes in and what comes out, nothing about the inside. For example, PickMe takes a pickup point and a destination and returns a confirmed driver. That is it. No mention of how. This is what you say to a customer or a product manager. It is the conversation you have first. The white box view. You describe how. The components inside, how they cooperate, what each one stores. Booking calls matching. Matching reads driver locations from the cache. Pricing computes the fare from the maps ETA. The result is sent back to the rider's phone. This is the conversation you have with another engineer or with the on-call team. Same system, different audience, different level of detail. Knowing which view to use with whom is part of being a professional engineer. New engineers often jump straight to white box and confuse non-technical stakeholders. Train yourself to start black box every time. Zoom in only when invited. Now I will introduce a very useful tool. It is called the C4 model. It is just a way of drawing software systems at 4 different zoom levels. Think of Google Maps. You can zoom out to see the whole country, zoom in to see a city, zoom in further to see a neighborhood, and zoom in even more to see a single street. C4 does the same thing for software. There are 4 zoom levels. Level 1 is called context. The whole system as one box, plus the actors and external systems around it. This is the level you can show to anyone, your boss, your customer, your grandmother. Level 2 is called container. We zoom inside the box. We see the web app, the API, the database, the queue. This is for developers. We will draw this on day 2. Level 3 is called component. We zoom inside one container. We see the modules and what each one does. We will draw this on day 4. And level 4 is code. Like a class diagram. We rarely draw this by hand. Tools generate it. Today we focus only on level 1. Context. The simplest and most useful diagram you will ever learn. A C4 context diagram has only 4 kinds of shapes. That is it. 4. Resist the temptation to add more. The first shape is people, stick figures with role labels. Rider, driver, operations agent. The second shape is your system. One big box in the middle with one name, PickMe platform. That is it. No internals shown. This is the black box view. We are not opening it yet. The third shape is external systems, other boxes, but shaded differently so a reader can tell at a glance. That one we do not own. Google Maps, payment gateway, SMS provider. The fourth shape is arrows. Arrows connect actors and systems. Every arrow has a verb-led label and we add the protocol so the reader knows the channel. Books trip via HTTPS. Charges card via REST. Sends OTP via SMS. 4 shapes, people, your system. External systems. Labeled arrows. That is a context diagram. Anyone can read it. That is the whole point. Here is what the PickMe context diagram looks like. At the top, 3 stick figures. The rider who books trips, the driver who accepts trips, the operations agent who handles issues. These are the human actors. In the middle, one big teal box. PickMe platform, that is the system in scope. We do not show what is inside it. That is for the next zoom level on a different diagram. At the bottom, 4 external systems, each in a dashed box, to make clear they are not ours. Google Maps for routing, payment gateway for cards and digital wallets, SMS provider for OTPS, push notification service for phone alerts, and in between arrows, going down from the actors to PickMe, going down from PickMe to the externals, each arrow with a verb, books, accepts, manages, routes, charges, notifies, and each arrow with a protocol. HTTPS. That is one diagram. about 10 boxes, about a dozen labeled arrows. And from this, anyone can understand what pick me is and what it depends on. This is the artifact you will produce in your first deliverable today. Let us pause and review what we have covered in the first hour. 5 words. That is the whole vocabulary of system design at this level. System, parts working together for an outcome. Component, one part with one job. Boundary, the line between yours and not yours. Actor, who or what calls in from outside. Interface, the agreed way to talk. If a friend asked you over lunch, "What did you learn this morning?" you should be able to use those 5 words in a paragraph and explain everything. The big idea is this. Before writing any code, you draw one diagram. That diagram shows your system as a single box, the people who use it, and the systems it depends on. That diagram is called a context diagram. Anyone can read it. Your manager, your customer, your future self in 2 months when you forget the project. That is the foundation. Now we move on to the second half of the day, requirements. In the second hour, we are going to look at requirements, what the customer actually wants from the system. Almost every requirement falls into one of 2 buckets. Beginners often forget the second bucket. Forgetting it is one of the most expensive mistakes in our industry. Bucket 1. Functional requirements, what the system does. A specific behavior the user can see. You can write a test that says pass or fail. Example, a rider can cancel a booking up to 2 minutes after it is confirmed. Clear, testable. Bucket 2. Non-functional requirements, how well the system does it, how fast, how reliable, how secure, how private, expressed with numbers, not adjectives. Example, the cancel button responds in under 500 milliseconds for 95% of taps. Both kinds matter. Functional requirements describe the behavior. Non-functional requirements describe the experience. A system that does the right thing but slowly is broken. A system that is fast but does the wrong thing is also broken. You need both, and you need them written down. Let us look at 6 functional requirements for a ride-hailing app like PickMe. Number 1. Rider can register with phone number and a one-time SMS code. Number 2. Rider can request a trip by entering pickup and drop-off addresses. Number 3. Rider can pay using card, EZ Cash, or cash on delivery. Number 4. Driver can accept or decline a trip within 30 seconds of being offered one. Number 5. Both parties can rate each other 1 to 5 stars after the trip ends. Number 6. Operations agent can refund a trip if the rider files a complaint within 24 hours. Notice the pattern. Each one starts with a person, says what they can do, and is specific enough that you could write a test by trying it. Pass or fail. No room to argue. That is what a good functional requirement looks like. Now the second kind, non-functional requirements. The rule is simple. If you cannot put a number on it, it is not a real non-functional requirement. It is a wish. Speed, how fast is fast? From tapping book to seeing driver assigned under 3 seconds for 95% of bookings. Now we have a target. Now we can measure it. Availability. Booking works at least 99.5% of the time over a calendar month. That is roughly 4 hours of downtime per month. Acceptable for some, not for others. Concurrency. Up to 2,000 riders can be booking at the same moment. That sets the scale we have to design for. Privacy. Rider home addresses are stored only inside our database. Never in logs, never in cache. That is testable. We can grep our logs. Cost. Average infrastructure cost per trip is below 4 Sri Lankan rupees. That keeps the business viable. Replace adjectives with numbers. Fast becomes under 3 seconds. Many users becomes 2,000 simultaneous. Secure becomes a specific compliance rule. That is the discipline. There is actually a third bucket I want to introduce: constraints. A constraint is a decision that has already been made before you arrived on the project. You do not get to argue with it. You design around it. Technology constraint. Must run on Azure App Service in the Australia East region. Why? The company already has the contract. You are not going to switch clouds because it would be slightly nicer. Budget constraint. No new tools that cost more than 50,000 rupees per month. Why? Finance approved that much, not more. Legal constraint. Must comply with Sri Lanka Personal Data Protection Act of 2022. Why? Because it is the law, not optional. Time constraint. Must launch before the Sinhala and Tamil New Year campaign. Why? Marketing already booked the advertising slots. Always list constraints separately from non-functional requirements. They look similar. They are different. Non-functional requirements you can negotiate. Constraints you obey. Knowing the difference saves you from arguing with the wrong people. Now let me show you a way to write the functional requirements. It is called the user story format. And there is a 6-letter test called INVEST that every good user story should pass. I stands for independent. The story can be built without waiting for another story to finish first. N stands for negotiable. The story captures what the user wants, not exactly how to build it. It is a conversation starter, not a design. V stands for valuable. A real user gets something useful when this story ships. Not just useful for the developer, useful for the user. E stands for estimable, clear enough that the team can guess how long it will take. If you cannot estimate, you do not understand it well enough yet. S stands for small, fits in a few days, not weeks. If it is too big, split it into smaller stories. T stands for testable. You can show the customer. You can write an automated check. You can prove it works or prove it does not. 6 letters, 6 tests. If your story passes all 6, it is ready to build. Here is the user story template you will use. As a persona, I want a capability so that an outcome. 3 blanks, persona, capability, outcome. Filled in for pick me, it might look like this. As a rider in Colombo, I want to cancel a booking up to 2 minutes after it is confirmed so that I am not charged a cancellation fee for a quick mind change. Notice what this story says and what it does not say. It says what the rider wants, cancellation within a window. It says why, to avoid being charged unfairly. The why matters. It tells the developer the spirit of the requirement, not just the letter. What it does not say. It does not say add a red cancel button on screen X. That is design work. It does not say store cancellation timestamps in a separate table. That is implementation. Those decisions come later. The story keeps options open. That is what negotiable means in INVEST. The story captures intent. Solutions are decided in design. Each user story comes with a small set of acceptance criteria. The most useful format for these is called given when then. 3 words, 3 parts. Given, the starting situation, what must be true before the user does the action, the setup. When the action, what the user actually does, the trigger. Then, the visible result, what the user or the system sees afterwards, the outcome. Crucially, this must be observable from outside. Not the function returns a promise. The user sees what? Why does this format matter so much? Because it speaks to 3 audiences at once. QA can copy the given when then directly into a test script. Developers can read it and know what to build. AI coding agents can implement it. 1 artifact, 3 audiences. That is leverage. Let us see given when then on the cancellation story. The story is, as a rider, I want to cancel a booking up to 2 minutes after confirmation so that I am not charged for a quick mind change. Acceptance criterion number 1. The happy path. Given a rider has confirmed a booking 90 seconds ago, and no driver has yet started the trip. when the rider taps Cancel Booking. Then the booking status becomes canceled, and no charge appears on the rider's account. Read that aloud. Anyone in the team can do exactly what it says. That is the test. Acceptance criterion number 2, the negative case. Given a rider confirmed a booking 4 minutes ago, when the rider taps Cancel Booking, then a cancellation fee of 100 Sri Lankan rupees is charged, and the user sees the message cancellation fee applied. 2 criteria: cover the success case, cover the boundary case. Now QA knows what to test, the developer knows what to build, and the customer knows what they are getting. That is the power of this format. Now I want to teach you something most engineers learn the hard way over many years. We will give it to you on day 1. When you read a customer brief, train your nose for 3 smells. Smell number 1, vagueness, adjectives without numbers. The system should be fast and easy to use. Stop right there. Fast how? Easy how? Replace with search results return in under 800 milliseconds. New users complete their first booking in under 2 minutes. Now you have something to test. Smell number 2, hidden assumptions, the obviously trap. The brief says the rider sees the price. But in what currency, after or before discount, including taxes? The customer assumed everyone knew. The developer guessed wrong, surfaced the assumption. The rider sees the final fare in Sri Lankan rupees, including taxes and any active promo discount. Smell number 3, embedded solution, design dressed up as a need. The brief says use RIDIs to cache the search results. That is not a need. That is a solution to an unstated need. Move it, restate the need. Repeat searches within 30 seconds should not hit the database again. RIDIs is one way. There may be others. The decision belongs in design, not in requirements. When you smell one of these, do not write code. Ask a question first. Now you put it all into practice. Let me read you the brief, exactly as the founder would email it. LearnLanka connects Sri Lankan O-level and A-level students with vetted tutors for one-to-one online sessions. Students should be able to find tutors by subject, language, and price. They should be able to book and pay and rate the tutor afterwards. Tutors set their availability and get paid weekly. We want it to be fast, secure, and ready before exam season. That is 1 paragraph, about 60 words, and it has all 3 smells we just talked about. Fast with no number, there is your vagueness. Secure with no specifics, same. What does secure mean here? Comply with what? Get paid weekly with no detail. Paid by whom, into what kind of account, in what currency? There is also a hidden assumption. Who can rate whom? Only students rate tutors, or both ways. The brief does not say. Your job in hour 3 is to take this paragraph and turn it into a clear requirements document, a context diagram, a user story set, and a list of clarifying questions. You have about 50 minutes. Aim for good enough, not perfect. There are 4 deliverables. Each is worth 25 points. Pass mark is 75 out of 100. The full rubric is in challenge.md. Read it before you start. Deliverable 1. The requirements document, personas, functional requirements, non-functional requirements, assumptions, and what is out of scope. Use the format we just learned. Deliverable 2. The context diagram. C4 level 1. Show the actors, your system in the middle, the external systems and labeled arrows. Deliverable 3. The user story set. At least 6 stories covering all 3 personas. Each story passes the INVEST self-check and has given when then acceptance criteria. Deliverable 4. The ambiguity log. Find at least 10 smells in the brief. Classify each one as vagueness, hidden assumption, or embedded solution. Add a clarifying question and a priority. For tools, use draw.io or Excalidraw for the diagram. Markdown for the documents. Miro for the workshop in hour 2 if you want to brainstorm with your pair. You do not have to be perfect. You have to be clear. Clarity beats cleverness every time. Well done, you have made it through day 1. You now know more about system design than you did at breakfast. Take a moment to feel that. Tonight, do 6 things to lock in what you learned today. 1. Read the C4 context page on c4model.com. It is short. Bookmark it. 2. Sketch a container diagram for LearnLanka. A rough hand-drawn version is fine. We will come back to this on day 4. 3. Pick any one of your user stories and write 3 negative test cases. What should fail and why? 4. Pick a real BISTEC product like BISTEC Care or Denstro, look at their public website, and write what you guess are their top 3 non-functional requirements. 5. Watch any 10-minute video about the difference between requirements and design. Post 1 good quote into the cohort team's channel. 6. Add 2 questions you still have about today into a file called learninglog.md. We will revisit those on day 5. Tomorrow, day 2 is about building blocks. A P is databases, caches, and queues. What each one is for and when to reach for which. We start at 9. Get a good night's sleep. See you tomorrow.